look at what are the content that we cover through this video lesson. Contents are: what is a thread, process, under processes, we talk about process states, drawback of processes, then introduction to threads, motivation for threads, advantages of threads, and drawback of threads. Then we'll talk about overview of threads, multi-threading modules. Under multi-threading modules, we'll talk about many-to-one, one-to-one, and many-to-many. Then threading issues. Under threading issues, we'll talk about thread cancellation, thread pools, signal handling, thread-specific data, schedule activations. Then fast multi-threaded C library. Under that, schedule initialization, schedule structures, thread API, user-level thread scheduling, user-level thread schedulers, thread management issues, blocking kernel threads, shared run queue thread scheduling, per processor run queue thread scheduling. Multi-threading in .NET 2.0. Under that, why multi-thread, thread timer, threads, background of threads, thread states, thread class, background worker class, thread pool, thread local storage, thread relative static fields, mutex, deadlocks, exception handling. Then Java threads. Under that, the thread object, thread creation diagram, runnable interface, thread lifecycle, blocking threads, thread scheduling, thread starvation, thread priorities, general strategies, thread conditions, thread synchronization, thread deadlock, avoiding deadlock, wait and notify. Under that, wait and notify code, wait and notify sequence, wait and notify details, wait and notify blocking queue. What is a thread? A thread of control is an independent sequence of execution of a program code in a process. Threads are inside processes, so let's focus on processes first. Processes. Why processes? Early computers allowed only one program to be executed at a time. Current computers allow multiple programs to be loaded into memory and to be executed concurrently. In a batch system, we call them as jobs or processes. What is a process? Process is a program in execution. Every process has a process control block, PCB. It includes program counter, PID, that is process ID, contents of process registers, stack containing temporary data, data section containing global variables. Process states. As a process executes, it changes its state. There are 5 different states: new state, ready state, waiting state, running state, and terminated state. New state. When a process is created, it occupies the new or created state. In this state, process awaits admission to the ready state. Ready state. Process moves to a ready state when it is loaded into the main memory and is waiting to be context switched onto the CPU by the dispatcher. Running state. A process moves to the running state when it is chosen for the execution. Waiting state. While process is being run, if an I/O event occurs or it goes to the waiting state. Terminated state. A process may be terminated either from running state by completing its execution or by explicitly being killed. Processes do not share memory, not even the parent process and the relevant child processes. Process control block is in kernel memory and it is controlled by the kernel. Drawbacks of processes. Process creation is very expensive. It needs more space from the main memory. For each process, it needs separate memory allocations. Context switching is more expensive. It stores data in PCB and reloads them from it later. Inter-process communication needs a lot of time because for communication, message queues or pipes or shared memory has to be created. Threads. Motivation for threads. In certain cases, a single application may need to run several tasks at the same time. Creating a new process for each task is time consuming. So, the solution is use a single process with multiple threads. A thread of control is an independent sequence of execution of a program code in process. A thread is a basic unit of CPU utilization. It contains thread ID, program counter, a register set, and a stack. Traditional processors have single thread. The context switching is the bottleneck of processors. Threads are used to avoid that bottleneck. Threads can be in several states. They are ready, blocked, running, or terminated state. Threads share CPU. Only one thread at a time can run. A thread within a process can execute sequentially. Each thread has its own PC and stack. Threads can create child threads. It can block waiting for system calls to complete. If one thread is blocked, another thread can run. Threads are not independent of one another. That is a major difference comparing with processors. All threads can access every address in the task. A thread can read or write over any other thread stack. Advantages of threads. Thread creation is less expensive than process creation. Process needs more space from main memory, but thread needs only separate thread control block (TCB). For each thread, no separate memory allocations. The time for creating a thread is significantly less than that for creating a process. Thread context switching is less expensive than process context switching because it has to store and reload less information such as thread ID, register content, and stack. Inter-thread communication is less expensive than inter-process communication because threads have been already shared memory. Drawbacks of threads. Threads are sharing data, so they are not independent. Access controlling, synchronization has to be provided. Writing multi-threaded programs require more careful thought, more difficult to debug than single-threaded programs. For single processor machines, creating several threads in a program may not necessarily produce an increase in performance. Only so many CPU cycles to be had. Overview of threads. Thread management is done by user-level thread library. There are two types of threads that are user-level threads and kernel-level threads. Some of the user-level threads are POSIX-P threads, C threads, Solaris threads. And the threads that are supported by kernel are Windows 95, 98, NT 2000, Solaris, True 64 Unix, BOS, Linux. Multi-threading modules, many-to-many, one-to-one, and many-to-one. Many-to-one. Many user-level threads map to kernel single thread, used on systems that do not support kernel threads. Examples are Solaris Green threads, GNU portable threads. One-to-one. Each user-level thread maps to kernel thread. Examples are Windows 95, 98, NT, 2000, and Linux. Many-to-many. In this model, the library has two kinds of threads. Bound. Bound threads are mapped each to a single lightweight process. Unbound. Unbound threads may be mapped to the same LWP, probably the best of both worlds, used in the Solaris implementation of pthreads and several other Unix implementations. Threading issues. Thread cancellation. Thread cancellation is terminating a thread before it has finished. Two general approaches of thread cancellation are asynchronous cancellation, deferred cancellation. Asynchronous cancellation terminates targeted thread immediately, and the deferred cancellation allows the target thread to periodically check if it should be cancelled. Thread pools. Create a number of threads in a pool where they wait work. Advantages of thread pools. Usually slightly faster to service a request with an existing thread than creating a new thread. Allows a number of threads in the applications to be bound to the size of the pool. Signal handling. Signals are used in Unix systems to notify a process that a particular event has occurred. A signal handler is used to process signals. Signal is generated by a particular event. Signal is delivered to a process. Signal is carried. Options. Deliver the signal to the thread to which the signal applies. Deliver the signal to every thread in the process. Deliver the signal to certain threads in the process. Assign a specific thread to receive all the signals for the process. Thread-specific data. Allows each thread to have its own copy of data. Useful when you do not have control over the thread creation process, that is, when using a thread pool. Schedule activations. Many-to-many models require communication to maintain the appropriate number of kernel threads allocated to the application. Schedule activations provide opcalls, a communication mechanism from the kernel to the thread library. This communication allows an application to maintain the correct number of kernel threads. Various implementations. pthreads, a POSIX standard, that is IEEE 1003.1c, API for thread creation and synchronization. API specifies behavior of the thread library. Implementation is up to development of the library. Common in Unix operating systems. Windows threads. Implements the one-to-one mapping. Each thread contains a thread ID, register set, separate user and kernel stack, private data storage area. The register set, stacks, and the private storage area are known as the context of the threads. Linux threads. Linux refers to them as tasks rather than threads. Thread creation is done through clone system call. Clone allows a child task to share the address space of the parent task. Java threads. Java threads are created by extending thread class or implementing the runnable interface. Java threads are managed by JVM, and the Java threads and the Linux threads will be discussed at the end. Fast multi-threaded C library. It provides scheduler initialization and shutdown, structures for scheduler, run queues, thread descriptor, communication constructs, provide functions for thread creation, execution, inter-process communication, yield, and destroy. Scheduler initialization. Traditional main function is part of library. The application programmer uses cthread main as main function. Initialize all scheduler data structures. Cthread main is in itself a thread. Scheduler structures. Thread run queue, fast first in first out queue, priority based scheduling, under that multiple queues and priority queues, thread descriptor, PC and set of registers, stack, pointed to chunk of memory, thread API. It provides functions for threads. Initialization, that is cthread init, execution, cthread run, yield, cthread yield, barrier, cthread join, termination, automatic. User level thread scheduling. Thread scheduling is abstracted from the kernel. Thread management occurs at the user level. No expensive system calls. Mini kernel on top of the OS kernel. Ideal for fine-grained multi-threading. User-level thread scheduling. Successful user-level thread schedulers exist in the form of CCSP, KROZ, MESH, MACH cthreads, SMASH, Sun operating system threads. Thread management issues. Interaction with operating system, blocking kernel threads, multiplexing kernel threads, schedule activations, system call wrappers, thread corporation, automatic yield insertion, active context switching, blocking kernel threads. In single kernel threaded schedulers, when the kernel thread blocks on a blocking system, call the entire scheduler blocks, multiplexing kernel threads. It reduces the problem, though the problem is still there, increases the amount of horizontal switching. Partial solutions. Allocate kernel threads for particular functions. Examples: keyboard, input-output, and horizontal switching. System call wrappers. Wrap all blocking system calls with wrappers that launch a separate kernel thread. Require wrapper for each call. Ideal when wrappers already exist. Incurs horizontal switching overhead. Blocking system call might not block. Shared run queue thread scheduling. Central run queues balance the workload equally among all processes. Threads are obtained from the shared run queue and serviced. Service threads are placed back onto the run queue unless they terminate. Shared run queues favor the principle of load balancing. Processor on queue thread scheduling. The processor on queue schedulers maintain a local run queue for each processor. The principle of locality is favored. Content is reduced because processors reference data close to it, thus reducing communication, which can lead to contention. Multithreading in .NET 2.0. Why multithread? To keep the UI responsive, to improve performance, for example, concurrent operation of CPU bound and IO bound activities, design logic, for example, to model independent real-world objects. Thread timer. The thread timer system.threading.timer is a simple, lightweight timer that uses callback methods and is served by thread pool threads. The thread timer's interval property is a long 64-bit integer and therefore is effectively unlimited. Under .NET threads we have background versus foreground, thread states, thread class, background work class, thread pool with thread data, modifying the UI, thread synchronization. Background threads. In .NET, a managed thread is either a background thread or a foreground thread. Background threads are identical to foreground threads with one exception. A background thread does not keep the managed execution environment running. Use the threads.isBackground property to determine whether a thread is a background or a foreground thread, or to change its status. Thread states. The thread state enumeration has a flag attribute that allows a bitwise combination of its member values. Aborted, aborts requested, background, running, stopped, stop requested, suspended, suspend requested, unstarted, wait, sleep, join. Once a thread is created, it is in at least one of states until it terminates. Threads created within the CLR are initially in unstarted state, while external threads that come into runtime are already in running state. An unstarted thread is transitioned into the running state by calling start. Thread class. You can create your own thread object or borrow one from the thread pool. Properties. Is alive, is background, is thread pool, manage thread ID, name, priority, thread state. Methods. Abort, interrupt, join, reset abort, resume, sleep, and suspend. Creating a new thread object creates a new managed thread. The thread class has constructors that take a thread start delegate or a parameterized thread start delegate. The delegate wraps the method that the new thread will invoke when you call its start method. Using parameterized thread start delegate is not a type-safe way to pass data because the system.threading.thread.start method overload accepts any object. An alternative is encapsulate the thread procedure and the data in a help class and use the thread start delegate to execute the thread procedure. Background work class. New in .NET 2.0, designed to simplify management of asynchronous operations for Windows Form applications. Automatically marshal communications between the UI and thread pools thread. For example, see Fibonacci calculator code. Thread pool. The thread pool provides your application with a pool of worker threads that are managed by the system. The threads in the managed thread pool are background threads. A thread pool thread will not keep an application running after all foreground threads have exited. The request that a work item be handled by a thread in the thread pool called the queueUserWorkItem method. This method takes as a parameter a reference to the method or delegate that will be called by the thread pool thread. There is no way to cancel a work item after it has been queued. There is one thread pool per process. The thread pool has a default size of 25 threads per available processor. The number of threads in the pool can be changed by the setMaxThread method. Each thread uses the default stack size and runs at the default priority. There are several scenarios in which it is appropriate to create and manage your own threads instead of using thread pool threads. You require a foreground thread. You require a thread to have particular priority. You have tasks that causes the thread to block for long periods of time. The thread pool has a maximum number of threads, so a large number of blocked thread pools thread might prevent tasks from starting. You need to place threads into a single threaded apartment. All thread pools thread are in the multi-threaded apartment. You need to have a stable identity associated with the thread or to dedicate a thread to a task. Thread local storage. The CLR allocates a multi-slot data store array to each process when it is created. The thread can allocate data slot in the data store and retrieve a data value in the slot, and free the slot for reuse after the thread expires. Data slots are unique per thread. No other thread can get that data. The allocate data slot and allocate name data slot static methods of the thread class are used to allocate slots. Name slot can be found with getNameDataSlot. Name slot can be freed with freeNameDataSlot method. Thread relative static fields. If you know that a field of your type should always be unique to a thread and application domain combination, decorate a static field with a thread static attribute. In all threads other than the first, the fields will be initialized to null if they are references type, or to their default value if they are value types. As a result, you should not rely on class constructors to initialize thread relative static fields. Instead, you always assume that thread relative static fields are initialized to null or to their default values. Mutex. A thread acquires a mutex by calling wait1 and releases it by calling release mutex. Mutexes have thread affinity. That is, the mutex can be released only by the thread that owns it. Because the mutex class derives from waitHandle, you can also call the static waitAll or waitAny methods of waitHandle to request ownership of a mutex in combination with other waitHandles. If a thread terminates without releasing a mutex, the mutex is said to be abandoned. In .NET 2.0, an abandoned mutex exception is thrown in the next thread that acquires the mutex. In .NET 1.0 and 1.1, an abandoned mutex is set to the signal state and the next waiting thread gets ownership. No exception is thrown. Deadlocks. A deadlock occurs when each of two threads tries to lock a resource the other has already locked. Neither thread can make any further progress. Some techniques to avoid deadlocks. Use timeouts on all attempts to acquire lock. Always acquire locks in the same order. Waithandle.waitAll method should be called. Exception handling. If the thread method completes its execution, .NET will shut down the thread gracefully. However, any unhandled exception thrown on the call stack of the thread will terminate not just the thread but also the trigger shutdown of the hosting process itself. The one exception to this rule is the thread abort exception, which will only terminate the aborted thread. This behavior is a breaking change introduced by .NET 2.0. In contrast, .NET 1.1 will only terminate the thread that encountered the unhandled exception. When porting .NET 1.1 applications to .NET 2.0, make sure that your thread method always catch and handle any exception. Otherwise, you'll risk unplanned application termination. Let's focus on Java threads. So far, we have discussed about to some extent on threads. Thread is not an object. A thread is a flow of control. A thread is a series of executed statements. A thread is a nested sequence of method calls. Let's look at the thread creation diagram. Object A is creating a thread object. It extends B thread class. Then the start method has been called. There, the thread is created. Then object A will run the other methods of it. After performing particular task, object B has terminated the thread. The runnable interface, a helper to the thread object. The thread object's run method calls the runnable object's run method, allows thread to run inside any object regardless of inheritance. This is an example of creating a thread objects with runnable objects. Implement a runnable interface in your own class. Implement the run method defined the runnable interface in your own class. Instantiate a runnable object of your own class. Instantiate a thread object of the thread class with the runnable object specified. Call the start method on the new object. The thread object is created with a special thread constructor which takes a runnable object as input. If you start a thread object created in this way, the run method of the runnable object will be executed as a new thread. Maybe you're wondering why we need this method of creating a new thread, which seems to be less straightforward than the other way. The answer is that Java classes cannot be extended from two different base classes. So if you're in a situation where you want to create a new class by extending an existing class to inherit some nice features of that class, and you also want to make a new class executable as a thread, you have to use a second way to implement the runnable interface in your new class. This is thread lifecycle. Initially, the thread is in born state. When the start method is called, it will go to the runnable state. It will go to the dead state when the stop method is called from born state or from the runnable state. When the suspend method or wait method is called, it will go to the block state. Then it will be gone back to the runnable state if resume method or notify method is called. Blocking threads. When reading from a stream, if input is not available, the thread will block. The thread is suspended until input or output is available. Allows other threads to automatically activate. When I/O is available, thread wakes back up again, becomes runnable, not to be confused with runnable interface. Thread scheduling. In general, the runnable thread with the highest priority is active. That's in running. Java is priority preemptive. If a high priority thread wakes up and a low priority thread is running, then the high priority thread gets to run immediately. Allows undemanding processing. Efficient use of CPU. Thread starvation. If a high priority thread never blocks, then all other threads will starve. Must be clever about thread priority. Race conditions. Two threads are simultaneously modifying a single object. Both threads race to store their value. In the end, the last one there wins the race. Actually, both lose. Here example of race condition. Let's go through it. Thread synchronization. Language keyword is synchronized. Takes out a monitor lock on an object. Exclusive lock for that thread. If lock is currently unavailable, thread will block. Thread text access to code, not to data. Make data members private. Synchronize accessor methods. Put a force field around the lock object so no other threads can enter. Actually, it only blocks access to other synchronizing threads. Thread deadlock. If two threads are competing for more than one lock, for an example, we'll take bank transfer between two accounts. Thread A has a lock on account 1 and wants to lock account 2. Thread B has a lock on account 2 and wants to lock account 1. Avoiding deadlock. No universal solution for that. Encapsulation, spawn new threads, check and back off, timeout, minimize or remove synchronization. Wait and notify details. Often the lock object is the resource itself. Sometimes the lock object is the producer thread itself. Wait and notify details. Must loop on wait in case another thread grabs the resource after you are notified before you acquire the lock and return from wait. Use lock.notify all method if there may be more than one waiting thread. This is wait and notify sequence. Have a look at it, then you get a clear understanding of how this wait and notify works. This is the wait and notify code activate and notify code for the consumer.
This is the Java code segment, and you can try this exercise on your own and see how it is run. This is the C# code segment. And this is the C code segment. If you want to get download these codings, you can always visit our